Okay, so today I want to present to you a theorem by Marco Brunella, and I want to continue to present examples to understand this theorem by Marco. Recall that we have foliation on theory, and the first example are linear foliation on theory, and we have said that in the generic case, if the torus is generic, this is the case where the field of meromorphic function is the complex number, then in this case, all the foliation on this complex theory are linear. There is a little problem here. Okay. So, this type of foliation on complex theory of linear foliation are well understood, and all the leaves of all the possibilities of leaves are classified, and the dynamic is following. In one case, every leaf of O foliation is dense in the ambient torus. The second possibility is every leaf is compact. In fact, is a compact torus, a subtorus of the big torus. Of every leaf is a codimension 1 subtorus. And there is another case, which is the following. Every leaf is dense in a real codimension 1 subtorus of the big torus, and you have the so-called Lévy flat phenomena. So it's a consequence of the description of compact abelian real Lie groups, in fact. There is a paper by Etienne Gis. In this paper, he gives a classification of regular, non-singular foliation on compact homogeneous spaces, in particular in Torah. And there is another paper. It's not possible to me to give the presentation of this theorem by Marco Brunella. And in this paper, Brunella classifies all the foliation on all tori with or without singular points. It's a little bit difficult to explain. I want here to give an example of foliation on a torus of dimension 2, which is not a linear foliation. Recall that if you have an elliptic curve, that is the quotient of C by a lattice, the classical notation is something like this, up to conjugacy, with omega or alpha, a complex number which is not real. And on elliptic curves, there are holomorphic function on P1, there exists a holomorphic function. In P1, there are the elliptic function. And in fact, there are meromorphic function. From C to C, which are periodic under the lattice. And the most famous is the Weierstrass P function, which is something like this. Omega is in the lattice. So I consider on the product of two elliptic curves an elliptic function in the one variable, if you want, on the first factors. And I consider meromorphic one form of this type, B Z1 dz1 plus dz2 in C2, and this B is elliptic, that means it's lambda periodic. And for B, you have pole, and you have 0. And I consider in so the torus is T2. I consider in T2 minus the poles of B. So the poles of B, it's a finite number of elliptic curve. In the big torus, and this is U1. And in U1, the form here, omega restrict to U1 is holomorphic. And I consider U2, which is torus minus the 0 of B, and the form omega, this is omega 1, for example, and the form omega 2 is omega, and I put in denominator B. And this form is holomorphic on U2. So you have the data U1, U2 with the form omega 1, omega 2, and this gives a foliation on the torus. And in fact, this foliation is given by a closed meromorphic form. This form is this form not. This form is closed. For men only. And this is an example of the so-called turbulent foliation, and I want to give a precise definition of turbulent foliation. But now I say that in this case, you have vertical elliptic curve in the product, which are leaves elliptic curve, finite number, the pole of the first form, for example. And there are other leaves, and the other leaves are turbulent in a certain sense, and I want to explain later this with the concept of holonomy. So there exists foliation on, for example, on algebraic theory, for example, product of elliptic curves, which are not linear. And the topology of the leaf is a little bit complicated. Now, I want to speak on foliation of manifold with these foliation are related to Frobenius Theorem in a certain sense. And I want to explain a little bit what is of manifold. And I consider a particular case of manifold. Take the space Cn minus 0. And take a complex number such that it's not on the unit circle. For example, condition like this. And you consider the group of linear map, which are the homothéties. And I consider this group act on this space, and I consider the quotient by G by G. And I denote this space by M and the dimension and rho the complex number. For example, if you take the sphere of codimension 1 in Cn, the real sphere, then the image by the homothétie rho is another sphere of radius exactly rho, here unit sphere. And if you want annulus between the two spheres is a fundamental domain. And this implies that the topology of this quotient is exactly the product of the sphere, the big sphere, product with S1. Here, if you take rho, for example, 1/2, this point is identified with this point, So this segment gives a circle in the quotient space. So you have something like this. For example, for n1, the quotient is an elliptic curve. Torus. And there is a fact which is the following. The lines by 0 are invariant by the homothétie rho identity. So this implies that you have a vibration from the Hopf manifold, Mn rho, on the projective space of dimension n-1, the space of line, and the fiber are elliptic curve. Now, I want to note the projection from Cn minus 0 by P, canonical projection. And now I consider foliation F on Mn. And I take the pullback by P, I lift, on Cn minus 0. This gives a foliation outside the origin of Cn. But if you have a foliation on Cn, codimension 1, foliation on Cn minus 0, this foliation extend to the origin. Yes. So recall that it's, for example, n greater than, no, yes. Recall that this first cohomology group is trivial. Then this implies that there exists a holomorphic one form omega global which defines, in fact, no, there is another argument, better, excuse me. Excuse me. At each point, M, at each point, you have a germ of form which gives all foliation. And it's of this type with holomorphic function. And now I consider the meromorphic function. Suppose that the first coefficient is not 0. So now you have a meromorphic form at each point which gives all foliation. And this meromorphic forms, this type of form is unique because the coefficient here is 1. This implies that there exists a form, meromorphic form, of type of this type, which at each point defines the foliation. And now you have Levy prolongation theorem. It's a variant of Hartogs in the case of meromorphic function. And the Levy prolongation theorem says that this form, this function a to Rn, in fact, are meromorphic at the origin. And this argument is good in dimension 2, and the previous argument with cohomology is not good in dimension 2. And this implies that you can extend the foliation at 0. You take omega, a form which is ad hoc multiple of omega, it's holomorphic in Cn, and define the pullback of f outside 0, if you want. And this form, the foliation, in fact, the foliation is on this space, and the foliation f tilde is invariant by homothétie, by the homothétie rho identity. And this implies that it is possible to choose, it's an exercise, to choose the form omega. You change the form by multiply by good unit, an homogeneous form. I note omega nu, and this omega nu is a combination of polynomial of degree nu. So, and now I suppose that the first foliation f on the Hopf manifold is without singularities. That means that the foliation f tilde has a unique singularity in 0. Without singularities implies f tilde is without singularities implies f tilde as eventually a unique singularity in 0. And now I say that we have something like infinitesimal Malgrange singular Frobenius theorem. That means theorem at order 1, if you want. It's the following. I take a homogeneous integrable form on Cn with singularity 0, or without singularity, if you want, 0. And I suppose that the dimension is greater than 3. Then the form omega nu is closed, in fact exact, the differential of a polynomial of degree nu plus 1. And the proof use commutative algebraic result, which is the so-called de Rham-Saito lemma, which says the following. We take, it's a particular case, just for our purpose. I take a germ of one form, alpha, and a germ of two form, beta, such that alpha wedge beta is 0. And I put a condition of the 0 on the singular locus of alpha. And the conclusion is that beta is a wedge product of alpha and one form theta. I want to give analytic proof just for you. It's not the classical proofs. Classical proof is something of algebra. At first, recall that if you have a local germ of one form and beta germ of two form, such that at M, such that alpha is not 0 and alpha wedge beta is identically 0. Then locally, there exists a germ of one form theta such that, like in the lemma. But here, I suppose there is no singularity. Beta is alpha cross theta. And the proof is easy. Take you take a vector field local vector field Z such that, for example, the interior product of alpha by Z is identically 1. And you take interior product of the three form alpha wedge beta. This is 0. And this is something like this is 1 plus minus alpha wedge Ez beta. I take this as theta. So the lemma is proved in the regular case, and now I give the singular case by cohomology. I take a polydisk, small polydisk, such that all the objects are defined in the polydisk. And the origin is here. And at each point, if you take small polydisk around a point M which is not 0, you can apply the first remark. That means that take U small polydisks here. That means that for the restriction of beta to the small polydisk here, you have a small theta theta is on holomorphic one form on U. And for the two, they are the restriction to U. So if I have another V with an M prime here, I take the same beta V is alpha V wedge some theta V. You take the difference, you have 0, and 0 is alpha restriction to intersection, and wedge the difference. And this implies that the difference, it's a linear algebra. The difference is multiple of what? Of alpha. But by construction, the HUV are cocycle, satisfy cocycle condition. So this is a HU minus HV, and you modify the theta, and you have now a global form. And this global form is well defined outside the point here. And my proof, my proof is in C3 with the singular locus of alpha is origin. And you can extend the theta by orthogs at the origin. But in general, the proof is completely an algebraic proof. So you have this Theorem division lemma, and I return to my problem of foliation of manifold of dimension greater than 3. Foliation F on this space without singularity. Then recall that you have an F tilde defined by homogeneous form with isolated singularity. You write the Frobenius integrability condition, and this implies that the differential of the homogeneous form omega nu is the product of omega nu with something, theta. And you can see that here the one possibility the coefficient of omega nu are polynomial of degree nu, and the coefficient of d omega nu are polynomial of degree nu minus 1. So necessarily this is 0. And now if you want to classify the holomorphic foliation without singularity on Hopf manifold of dimension greater than 3, it is sufficient to know some little thing on polynomial, on singularities, on polynomial, on function, for example, Milnor's theorem, something like this, and to classify. Okay. One remark. So the leaves of the foliation on the Hopf manifold are you have in Cn you have, for example, imagine a quadratic form. So you have the leaves of the quadratic form C3. You project on your Hopf manifold, and this cone, quadratic cone, is ruled. All this line gives here elliptic curves. So there is a special surface in this case, which is an elliptic surface. That is a surface ruled by elliptic curves, which is a leaf, a compact leaf of the foliation here. Okay. We have the projection in the same hypothesis of the 0 of our polynomial. And this gives compact leaves, compact elliptic leaf. And the other leaf are the projection of the general level set. And in fact, these leaves, the closure of these leaves are the leaves plus the compact elliptic leaves. So you see there is a special leaf which is an image of the cone. P nu plus 1 is 0. And all the leaves accumulate these special leaves. And remark also that the form, meromorphic form, differential, logarithmic differential of the polynomial homogeneous P nu plus 1 is a form on the Hopf manifold, but with pole. Just a remark. To my knowledge, these things are not written. If you want to make a short note in Crass Academy, it's possible to write this, and you have a small paper. There are other Hopf manifold, a little bit complicated, and it's possible to make a theory, something like this. And in dimension 2, the study is a little bit more complicated than in dimension 3. Now, to understand the Marco-Brunella result, it's convenient to speak about holomorphic fibration on foliation. The situation is the following. It's like in the up case. You have a manifold of dimension n, and you have a fibration, excuse me. It's good? Yeah. So you have a fibration on from n m to n, p, morphism, and the dimension is of the basis is n minus 1. So the fibers are curves. Riemann surfaces. And I suppose that in this case that everybody is compact. For example, product of n by a Riemann surface of dimension 1. Example P1, for example, elliptic curve. And now I consider a foliation, an holomorphic codimension 1 foliation on M. And I say that the foliation is transversal to the fibration. You have M here. You have the fibers. And I want that at each moment, at each point, the leaves are transversal to the fibers of the fibration. That means if the foliation is locally given by one form omega y on u I, you take omega e at this point m, you take the kernel of this linear form, and you want that the tangent space red of the fiber is not in this kernel, is transversal. Tangent space m to the fiber. And we want this at any point. This is the definition of foliation, which is transversal to a fibration. It is not very difficult to prove the following. If you take a leaf, it's maybe something complicated, maybe something which is dense in the space M, but you can restrict. So this is a leaf, and you restrict the projection to the leaf L, and it's not difficult to prove that the restriction is a covering. The covering map. And now I fix a point, basis point. You see that, for example, if the basis is simply connected, the leaves are graph. something like this. So now it's a little bit difficult. And so I take basic point in N. I did not by, I don't remember. Yes. So here you have N and a point, basic point. Here you have the fiber. You have the fiber which is a compact Riemann surface in M. You take a point here, Y, and you take a loop, gamma, at the point X node. You have the leaf passing by the point Y, but these leaves, so the restriction of the projection P is a covering map, so it's difficult to make a picture. So you can lift gamma in the leaf. And you obtain another point. And I denote this point by H gamma of Y. And it's not difficult to prove that this lift, so this is gamma tilde in my transparent, it's not difficult to prove that this point don't depend of the depend only on the homotopy class of gamma in N. That means that if gamma is in the fundamental group in X node, then H gamma Y is well defined, if you want the class is well defined. And by implicit function theorem, the map of the fiber to the fiber will give H gamma of Y is holomorphic. Is an holomorphic map. And in fact, this H gamma is an automorphism of the fiber. Because if you make the construction with the inverse of gamma, you obtain the inverse of H gamma. So you have a so-called holonomy representation which is a map from the fundamental group to the automorphism of the fiber I denote by sigma, which is a morphism of group. But maybe now a remark. If you have a vibration like this and a foliation which is transversal to the vibration, and F transversal to P, then all the fibers are isomorphic. For example, if the fibers are elliptic curves, all the elliptic curves are the same. The modulus is constant. It's an exercise for you. Now I take now 2 points. I take 2 points in a leaf. I take 2 points in a leaf. In the same fiber. In the same leaf. A leaf is by definition connected, so you can make a path with go from y to y prime, and the projection of this path is a loop in N. So the intersection of the leaf L by E through the point Y with the fiber is exactly the orbit of the holonomy group so maybe I give something like rho, so orbit of, and G is a pi 1. So orbit of the point Y. So if you want, you have something like a discretization of foliation. We want to describe the leaves. The leaves are very complicated. You take a transversal in this case, and you have now a problem of usual dynamical system. It consists to describe the orbit of point by a certain group of Riemann surface. Now, I recall some facts on compact Riemann surface. Recall that compact Riemann surfaces, you know P1, you know elliptic curve, genus 0, genus 1, and you know hyperbolic curves or Riemann surface, genus greater than 2. And here I put the group of automorphism. So this is sigma. And you know this is the linear group PGL2C, which is a quotient of GL2 by the torus homothétie. Here, in general, the automorphism of elliptic curve are the translation and the involution in the generic case, but there are two examples which are the elliptic curve given by Gauss numbers and the hexagonal lattice. But in all the case, the automorphism group is a finite extension of the curve with its multiplication addition. And for genus greater than 2, in general, there are no automorphism identity. And in all the cases, the group is a finite group with, I don't remember the number, maybe something like, don't remember, something like this. But it's a finite group in all the cases. And generically, if the curve is generic, there is no non-trivial automorphism. And these facts are consequence on foliation. I give now the consequence. It's something with yes. Okay. The first example is with so foliation which is transversal to a vibration P, and I suppose that the fiber sigma has genus greater than 2. This implies that the image of the holonomic group is a finite group. This implies that if you take a transversal to a fiber, for each leaf, the intersection of this transversal with the leaf is a finite number of points, maybe something like this. And in fact, this don't depend of the choice of the point X node. Then at each moment, for each fiber of the projection P, the intersection of any leaf with this fiber is finite. This implies that all leaves are compact leaves. And in fact, there exists a function, holomorphic function, in the fiber. So, the holomorphic function in P1 such that the leaves are essentially the fibers of F. In fact, the connect component of the map, holomorphic map F. So now, in this case, the description of foliation which are transversal to the fibration with a fiber which is hyperbolic is the same theory with the study of the function with value in P1. Remark that this theory can be made with non-compact n. It's possible, it's the same. But it's more easy when M is compact. I give an example. Everybody knows Riccati differential equation. So what is a Riccati differential equation? I consider the ordinary differential equation. Y prime is R y2, b, y, c, and the a, b, c are holomorphic functions on, for example, connected open set U in C. And to this differential equation, we associate foliation F on the product of U by C. And it's a physics, the argument of physician. Which says that identification of derivation and forms. So we associate this differential form on the product U by C, and this form gives the foliation, and the graph of the solution of the initial equation, in fact, are local leaves of the foliation given by this one form. And I say that it's easy to extend this foliation on U cross P1. Maybe I make the exercise by using the chart of P1. You think that y is in C in P1, and the other chart is 1 over y. So if you make the change of coordinate here, so you have something like this. You put 1 over y here. If you want the foliation, this form is given by this form on C cross U. And this is the space of Yx. And now I take on the other chart, I multiply by Y2, and you have a new form. I have a new form. And it's, in fact, put Z in place of Y, but for the calculus, it's more easy to. And this is in the domain C cross U with Z, which is 1 over Yx. So this is the two data for the foliation. So this is a Riccati foliation. And you have the canonical fibration from projection on U. And the foliation is transversal to the fibration U cross P1 or P1. So this is X. And the foliation is transversal to the fibration P. And the reason is that the coefficient here and here are non-constant, non-zero constant, excuse me. In particular, you obtain an old theorem, I don't remember, maybe Malquist, or I don't remember, which says that if you have a domain U which is simply connected in the complex plane and the Riccati differential equation, then the solution of the equation are meromorphic. It's an old, in Valiron, for example, you have this theorem. Malquist? Bernard? Malquist, non, c'est plus vieux peut-être. C'est plus vieux. Hein. C'est peut-être. Hein? Pingevé savait ça, mais Malquist a fait des choses qui tournaient autour de la généralisation de ces choses. Other example of foliation which are transversal to fibration the previous example on the product of elliptic curves with another notation or the same notation, I don't remember. And you take this foliation on the product of elliptic curves, and you consider the pole of A, which are elliptic curve, and which are leaves of F. And now N is non-compact. It's an open set in the first elliptic curve. It's the first elliptic curve minus the pole of A, you see. And the projection is a natural projection. It's a first projection P1. And now I say that the foliation restricted to the N cross C, the second elliptic curve, is transversal to the fibration. And in particular, it's now possible to give a description of the leaves because you know the holonomic group. You have 2 or 3 elliptic curves. So you have first an elliptic curves, and you have the poles of A, and the fibers are elliptic curves here. On my picture, there are 3 elliptic curves. And these 3 elliptic curves are special leaves. I suppose that there are no other pole, and I take a point, a base point. I take the fiber by P minus x is 0. And now I compute the fundamental group of the torus minus point. And I lift now, I take a point here in the fiber. I lift this loop, and I construct the holonomy representation. And we know now that the trace of a leaf is exactly the orbit of the holonomy group on this elliptic curve here. And you have the classification of all the possibility of orbits, finite, non-finite, dense, no dense. So it's possible to give the list of all possibilities of leaves in this situation. It's a long way. And as I say, this is a particular case of turbulent foliation. I want to define now the concept of turbulent foliation. It's a generalization of on the blackboard. Yes. Turbulent foliation. But, okay, turbulent foliation. The context is the following. So you have a fibration, special fibration, because the fibers are elliptic curves, like in the example here. All the fibrations are elliptic curves. In N, you take an hypersurface H, think to the blue points, which are the hypersurface in this case. take an hypersurface in N, and you take a foliation F. The foliation is on N, and we suppose that the pullback of the surface H is a union of leaves. That means invariant by F. That means that P minus 1H is a union of leaves. In this case, it's the 3 special leaves. And outside this special leaf, I suppose that the foliation F restricted to the complement of the pullback of H, is transversal to the vibration. You see, it's exactly the example here. That is the definition of turbulent foliation. So you think to the example. So I give example of turbulent foliation. And the first example is the off-manifold with a foliation without singularities. For example, in dimension 3, you have a polynomial, you have a vibration. For example, you have a vibration on projective space with fiber elliptic. And the foliation on Cn is given by the level set of a homogeneous polynomial. There is a special level which is level 0. And when you descend here the special leaf, the leaf is invariant by the foliation. So you have now something like this. This is the projection of this cone. And this is a leaf. And outside this leaf, you have fiber which has elliptic curves, and the foliation is transversal to this family of elliptic curves. So this is an example of turbulent foliation. In case dimension 2 is a little bit more complicated than in dimension 3 and 4 and so on. Maybe tomorrow I give other example, because now I want to give the Markov theorem. Markov theorem. Markov theorem is the classification of holomorphic foliation without singularities on compact algebraic surfaces. That means surfaces which can be embedded in a projective space. So you think that you have a surface S, which is compact and in fact algebraic in a P big N. And we suppose that you have a foliation on this surface. So the theorem is in Anal école normale supérieure. So let X be a compact complex algebraic surface and an holomorphic foliation without singularities on x. And there is a list of possibilities. The first possibility that is f is a vibration. That means that you have your surface x in the transparent, and you have a projection on a Riemann surface, curve, compact, and the leaves are the level set of P. I give not the data for define the foliation, I give directly the leaves. The leaves are the level set of P. The first, it's a trivial case, if you will. The second example is the foliation is transversal to vibration. For example, Riccati differential equation, something like this. The third example is a turbulence. F is a turbulence foliation on an elliptic surface. An elliptic surface is a surface with a fibrillation by elliptic curves. So in this case, no. There are special fibers which are leaves, maybe. The fourth example is foliation on complex torus, linear foliation on complex torus of dimension 2. And another example, which is a little bit complicated, and I want to give an example. F is a transversally hyperbolic foliation with dense leaves on universal covering fibrillation. I want to explain what's this. There are surfaces with, I give an example, not the definition because it's a little bit complicated. I consider the Poincaré disk remember that the automorphism group is a group of real homography, and I consider the product of two exemplars of H, and they are surfaces which with universal covering this space. For example, there are the famous Hilbert modular surfaces. There are surfaces X. And you can take a discrete group which act on each of the factors. And you take, for example, foliation of x tilde by the horizontal. And this foliation goes to x to give a foliation on X with the property of density of leaves and so on. But it's a really complicated example definition, and the classification is not known of this type. So this is Marco's theorem. It's a big and difficult theorem. So, okay, maybe 5 minutes to return to. Okay. I want to speak a little bit on foliation of projective space. And to give another example of turbulent foliation. I want to speak about homogeneous integrable form in the general case. Recall that we have indication when the singular locus is reduced to 0 in dimensions 3, for example. Infinitesimal Lagrange theorem. So I considered an homogeneous integrable form, and there is naturally a foliation which is associated to this form, and this form is invariant by the action of the group of homothéties, because the form is invariant by this homothéty up to multiplication. So the kernel of the form is invariant. Notation, the radial vector field is this vector field related to Euler condition, and the trajectories of this vector field are the lines by the origin minus the origin. Okay? So just definition. And there are two cases. The first case is when our form or differential form annihilate the radial field. That means in this case all the lines by the origin are in the kernel of the form at each moment. That means that, in fact, the foliation of given by this form on Cn goes to the projective space, Pn minus 1. And there is an old terminology which says that the form is dicritical. It's a terminology by Darboux, by Pinlevé, by Auton. In the other case, foliation is to be said non-dicritical. And there is a lemma which is a generalization of the previous lemma on form with isolated singularities, which says that if your homogeneous form is non-dicritical, the quotient, the meromorphic form, maybe I give in coordinate if you want. The form is a sum of homogeneous polynomials like this. the interior product by the radial is something like this. And this is the polynomial p nu plus 1. And the lemma says that if this polynomial is non-zero, this form is closed. Maybe tomorrow, the proof? Okay, tomorrow.